Welcome, everyone. I'm excited to introduce today's presentation on machine learning, focusing specifically on the Candidate Elimination Algorithm. The Candidate Elimination Algorithm, or CEA, will explore how it works to find all hypotheses consistent with our training data, forming what we call the version space. We'll look at how it maintains two key boundary sets: the specific boundary, which includes the most specific hypotheses fitting positive examples, and the general boundary, which contains the most general hypotheses fitting negative examples. Any hypothesis that falls between these two boundaries is considered a valid candidate. Over the course of this presentation, we'll dive into each of these concepts in more detail. So let's get started. Let's walk through a step-by-step explanation using the classic enjoy sport example. The goal here is to understand the conditions under which a person is likely to enjoy their favorite sport. On this slide, you'll see a table with a few different examples. Each row represents a different scenario with various weather conditions and the corresponding outcome, whether the person enjoys the sport or not. For instance, look at the first example where the sky is sunny, the air temperature is warm, humidity is normal, wind is strong, and water is warm. In this case, the forecast is same, meaning conditions haven't changed, and the target concept is yes, indicating enjoyment. Notice how each example varies in conditions like rain, cold temperatures, or high humidity, and how these influence whether the person enjoys the sport. The key idea here is that by examining these examples, we can start to identify patterns: what conditions tend to lead to enjoyment and which do not. This process helps us understand the underlying rules or concepts that determine enjoyment based on weather factors. Throughout this presentation, we'll see how this example illustrates the fundamental process of learning concepts. By analyzing examples and their features, we can infer the conditions that define the target concept, in this case, enjoying the sport. Let's start with step 1, initialization. Here, we're working with a hypothesis that has 6 attributes. The idea is to set our boundaries for the hypothesis space right at the beginning. First, we have the initial specific boundary, or S0. Think of this as the most restrictive hypothesis possible. It accepts no examples at all. It's represented as meaning all attribute values are empty or undefined. This makes sense because, initially, we don't want to accept anything until we learn more. On the other hand, we have the initial general boundary, G0. This is the opposite. It's the most inclusive hypothesis, accepting all possible examples. It's written as where each attribute can be anything, any value, any combination. Now, why do we start here? Well, it sets the stage for the learning process. We begin with the most specific hypothesis that rejects everything and the most general that accepts everything. As we see more data, these boundaries will tighten or loosen, helping us zero in on the true hypothesis. This initial setup is crucial because it frames how the learning algorithm will refine its hypotheses over time, connecting directly to our overall goal of effective concept learning. Let's take a look at step 2 with example 1, which is D1. So D1 is a set of attributes: sunny, warm, normal, strong, warm, same, and it's labeled as yes. When we update our G, which is our version space for positive examples, we see that G0 was initially very general, accepting everything, so it's already consistent with D1. That means G1, our new generalization, stays the same. It remains as it was because it's already compatible with this example. Now, moving on to our S, which represents our specific boundary. Initially, S0 was too restrictive. It rejected D1, so it wasn't consistent with our positive example. To fix that, we need to generalize S0 just enough to include D1, making it as specific as possible while still covering this positive instance. This leads us to S1, which becomes exactly the attribute values of D1: sunny, warm, normal, strong, warm, same. This step ensures our version space accurately reflects the positive example without overgeneralizing. It's a crucial part of refining our hypotheses as we process more data, keeping our model both accurate and efficient. Now let's look at step 3 with example 2, or D2. Here we see a specific input: sunny, warm, high, strong, warm, same, which leads us to a positive classification of yes. First, we check the consistency of our current version space. We find that G1 is still consistent, and notably, G2 remains unchanged from G1. Next, we need to update our specific boundary set. We notice that S1 is inconsistent because it has a contradiction in the humidity attribute. In S1, humidity is normal, but in D2, it's high. To resolve this, we generalize S1 by replacing the differing attribute with a question mark, which indicates any value. This way, we acknowledge the inconsistency and allow for more flexibility. So after this update, S1 becomes more generalized. Normal is replaced with, meaning it can now match either normal or high. Consequently, our set S is now updated to include this new generalized example: sunny, warm, strong, warm, same. This process highlights how we refine our boundaries when faced with conflicting information, ensuring our model remains both accurate and adaptable as it learns from new data. Now let's move on to step 4, which is about process example 3, or D3. In this step, we're updating our S and G sets based on the negative example D3. First, we look at our current S, which is S2. Since D3 has a sky attribute of rainy and S2 requires sunny, S2 correctly rejects D3. That means S2 remains consistent, and we set S3 equal to S2. Next, we examine G, our generalization set. G2 was too broad because it accepted D3, which is incorrect since D3 is a negative example. So G2 is inconsistent, and we need to refine it. To do that, we remove G2 and generate new, more specific generalizations, what we call minimal specializations, that exclude D3 but are still more general than S3. Specifically, we focus on the attributes that differ in D3. The sky attribute is rainy, but to exclude this, we specialize the in G to any value except rainy. So for sky, we change it from to sunny. Similarly, for air temp, which is cold in D3, we change to warm to exclude cold. For water, which is warm, we change to cool. And for forecast, which is change, we change to same. This way, our new G3 set contains these specialized patterns: sunny in sky, warm in air temp, cool in water, same in forecast. These new generalizations correctly exclude the negative example D3, while remaining as broad as possible otherwise. This process of specialization ensures our model becomes more accurate by refining the concept boundaries based on negative examples. Now let's move on to step 5, which is process example 4, or D4. In this step, we look at how we update our hypothesis set, G, based on a new example. The example we're working with is sunny, warm, high, strong, cool, change, which leads to a positive outcome, yes. First, we need to update G by removing any hypotheses that are inconsistent with this new example. For instance, any hypothesis that requires a same in the last attribute, but the example shows change, is incompatible. So we eliminate those. Specifically, the hypothesis doesn't fit because our example has change there. So we remove it from G. After this removal, our updated G, which we call G4, contains hypotheses like sunny, warm, and cool. Next, we look at our version space. As previously, in S3, there was an inconsistency because the water attribute and the forecast attribute had conflicting values in the hypothesis and the example. To fix this, we generalize S3 by replacing the differing attributes with, which is a wildcard symbol that represents any value. So for water, since the example is warm and the hypothesis was perhaps more specific, we now use, indicating that water can be any value. Similarly, for forecast, which changed from same to change, we also replace it with. This results in S4, which is sunny, warm, strong. Overall, this process helps us refine our hypotheses and space, ensuring they are consistent with new examples while keeping our models as general as possible, without losing accuracy. Now, let's look at the final result of our version space. Remember, The version space includes all hypotheses that are consistent with our training data, lying between the most specific and most general boundaries. On this slide, we see the final specific boundary, labeled S-final. It's represented as a single hypothesis. Sunny, warm, unknown, strong, unknown, unknown. This hypothesis is quite specific, meaning it makes concrete predictions about some attributes while leaving others unspecified. Next, we have the final general boundary, G-final, which consists of 3 hypotheses. One states that the sky is sunny. Another specifies that the air temperature is warm. And the third indicates that the water is cool. Together, these G hypotheses define the broadest constraints that are still consistent with our data. Now, what does this all mean? Essentially, the target concept, which we call in JoySport, must be a hypothesis that is more general than S-final but more specific than all hypotheses in G-final. From S-final, we see that the concept must require the sky to be sunny, the air temperature to be warm, and the wind to be strong. These are the necessary conditions derived from our most specific hypothesis. However, because the final concept has to be less specific than the hypotheses in G-final, it must satisfy the condition that it is true if any of these attributes match. The sky is sunny, or the air temperature is warm, or the water is cool. This is a key point because it shows how the version space narrows down the possible hypotheses by balancing specificity and generality, helping us pinpoint the most accurate concept that fits all our data. Thank you for watching. Like, share, subscribe to EC Learning 360 YouTube channel.